This, ladies and gentlemen, is the physicist Richard Feynman, and he once described science as an expanding frontier of ignorance. Now, for scientists working on the front line, not only of their own frontiers of ignorance, but the frontier of ignorance of humanity itself, it can be a really daunting place to exist, staring out essentially into an abyss. But students of science also have this sense of being on their own expanding frontiers of ignorance. And our job as educators, essentially, is to try and help them to expand those frontiers. Why? Because out there are islands with discoveries and possibilities for us to perhaps go out and reach. How do we get there? How do we expand our frontiers of ignorance? Well, it turns out that scientists and students of science have a very powerful tool at their disposal. There's the question, what if? And I'd like to share this evening a bit of a story to do with what if, my own personal what if story. And it concerns the alkali metals. These are the group of elements that live on the left-hand side of the periodic table. People tend to remember them from school for their very dramatic reactions with water. And when we're at school, we try and explain the way in which they react using a simple model to help us understand what's going on. We imagine that we have small positively charged balls, we call ions, surrounded by negatively charged electrons. And the way that they sort of hold this whole structure together is to have these negatively charged particles and the positively charged particles attracting one another, much in the same way that you might rub a balloon on your head and stick it up against the wall. And as we go down the group, we find that actually that these ions, the atoms themselves, they get bigger. And so we might predict that in these reactions in which electrons are lost from the metal, we would expect, therefore, as we go down the group, just like rubbing a balloon on your head and holding it a little bit further away from the wall, it might fall off. It may not stick onto the wall at all. And in the same way, these electrons, as we go down the group, may be lost a little bit more easily. And this is where I began my what-if journey. Here's me at school with suspiciously similar handwriting to that of Richard Feynman, it would turn out. And an obvious what-if question perhaps came to mind. We'd already seen the reactions of lithium, of sodium, of potassium, and I wanted to work out, well, what if we were to put cesium in water? Surely that should be a lot more exciting, right? Now, my chemistry teacher, much like me as a chemistry teacher now, had neither the resources at hand nor the inclination to demonstrate this to me, but he did have a video to help me to perhaps understand what might happen if you add sodium to water. Thankfully, we didn't try that in the classroom. So, yeah, maybe cesium is going to react a lot more violently with water. But it turns out that with science, it's not good enough to just do an experiment once. You've got to try it more than once. And this is where I'd like to introduce you to the team of the Periodic Tables video channel from YouTube. They work at the University of Nottingham, and they decided they wanted to repeat this experiment. You can see here they were a little bit nervous about what was going to happen. They've got a contraption. If it's not clear, we've got a hammer hanging from a wall with a very long piece of string. They're ready for something big to happen. Let's see what happened when they put cesium in water. Oh. Is that it? Okay, so that wasn't quite as dramatic as we just saw. Now, at the time, they put this down to a bit of bad luck, because we know from the textbooks that this reaction is supposed to go explosively, right? I mean, something perhaps must have gone wrong. We better do this reaction one more time. Let's just, for comparison, make sure we've got a clear baseline to see what we're looking at. First, we'll have a look at their reaction of potassium on the top. Should be less dramatic. Took them by surprise. Nearly took out perhaps an arm or a leg at the same time. They then went back and they, right, let's get cesium right. This one is going to be big. we're going to not just use that same amount of cesium we had before, we're going to throw in 5 times the amount. We're going to prime this little puppy to go. We're going to get it out of the glass, no sticking. This guy, stand back, it's going to be big. Bit of a damn squid. 5 times the amount of cesium, but it's meant to go more explosively, right? Those electrons and stuff, it's further away. That's got to be what's going on. Now, for anybody who has been paying attention, something isn't adding up. And somebody who was paying attention a while ago, back in 2006, was one of my chemistry heroes, Theodore Gray. This guy is the sort of guy who acquires a large quantity of sodium off of eBay, invites a bunch of his mates around and throw it in a lake for a laugh. Now, he wanted to, again, scientifically test what's going on with cesium. This should be big. And once more, he was disappointed. You can see him here with the contraption that he made to detonate some cesium, this time underwater, to make sure it was really all going. It's supposed to be explosive, right? But he asked himself, after disappointment after disappointment after disappointment, what if the reaction of cesium isn't really that violent, despite what the textbooks would say? And his idea was remarkably simple. In fact, it had been staring everybody in the face, because any school leaver, they're supposed to know that the atoms get bigger as you go down the group. But of course, they also get heavier, which means that if you have 1 gram of lithium and you have 1 gram of cesium, if the cesium atoms are heavier, then there are going to be fewer atoms of cesium. You're going to produce less hydrogen, and therefore, perhaps, it might be less explosive. So we can see on my ever so fashionable graph, we love graphs in these kind of talks, on the left-hand side, the volume of the hydrogen that's being produced by the same mass of lithium, much greater than that of the cesium. The line going up here showing how much easier it's getting to remove these electrons. Theodore's idea, I think there might be a sweet spot here in the middle, somewhere around sodium or potassium. But there were 2 weaknesses in his idea. Number 1, look at the massive difference in the amount of hydrogen being produced. It can't all be down to that. And number 2, his idea was that it was the hydrogen gas burning, causing the explosion. Let's take a close look at one of these reactions. Some solid dropped in. Boom. No flames, no oxygen. The solid just atomizes. Something else is going on here, ladies and gentlemen. Because, as it turns out, chemistry is not just about the energetics of a reaction. For those of you who own any diamonds, I have some disappointing news for you. Chemistry, but specifically the study of thermodynamics, tells us that all of those diamonds right now are turning into worthless pencil lead, graphite, in your purses right now. Lady on the row 3, seat number 4. Okay, we'll have a read up. It's not about, though, just whether or not it's going to happen to this lady's diamonds down here at the front. It's about how fast it will happen. And actually, as it turns out, nobody's got anything to worry about, because this reaction to turn our beautiful diamonds into graphite happens far too slowly for it to be of any concern for us. This is where lithium steps in and says, I'm just going to take my sweet time. Okay, I'm going to produce the most heat in the reaction. I'm going to produce the most hydrogen. I'm just not going to do it very quickly. Why? Well, we've got all kinds of effects going on here. We've got its buoyancy, we've got its low melting point, which keeps its temperature from getting too hot and allowing the reaction to speed up still further. We've got the fact that the product that's being produced from the reaction dissolves the slowest. It just takes its time. It's not just down to the electrons, it's how fast we can get them across. Here I'd found myself on the edge of my frontier of ignorance. It felt pretty good. Hey, all this stuff, it may seem as if it's just simple textbook stuff. There's a lot more to be thinking about. Of course, that led me back to my original question. When I was young, I'd been watching this video, now described, literally, I kid you not, on YouTube as the accurate version of this reaction. And being a bit of a chemistry geek, I spent some time tracking down the guy who made it, was it close to 50 years ago now, who was a bit confused as to why this guy from Austria was trying to get in touch with him through about 4 or 5 different people. And he very kindly agreed to go back and look at the original footage again and every other piece of footage that he gathered. And at that time, decided to say, look, I'll be honest with you, actually my impression was, and has always been, that there's really no detectable difference between rubidium and cesium. We took a large number of clips on that day. The drama in that clip was purely a matter of luck. Doesn't mean, of course, that there was no reaction. It's just, of course, we were going to put the best one in the video. We wanted it to be popular. So I asked myself, well, what if no one actually has any idea what's going on with these explosions? Because now everything, my entire worldview has been torn apart. So I start trying to work out what's going on with the actual explosion then. The traditional view, as explained here by Martin Polyakov, again at the University of Nottingham, is, as we can see just at the bottom here, it's a vapour explosion. Sounds fancy. It's very simple actually. What it is, some very hot stuff. Here we have some very hot salt, rapidly boiling water. When the water comes into contact with it, that water vapour takes up a lot more volume, bursts through the rest of the really hot stuff, bringing more water into contact with it. In this case, boom. That's well and good, isn't it? Apart from the fact that all we need here is for some hot stuff. It doesn't really matter whether our electrons are easily lost or not, but we are seeing some kind of difference going on with our metals. And secondly, if we take a close look, we have solid potassium coming in here. Forget getting hot enough to reach the superheat temperature of water. It's almost instantaneously exploding. Now, when I saw this video clip, ladies and gents, I knew I had to get in touch with the guy who'd been making it. Now, a guy by the name of Phil Mason, who has a YouTube channel, Thunderfoot, and he'd been experimenting with some high-speed cameras and the alkali metals. And the reason that I got in touch was because I had been furiously Googling in the meantime. And what did I find? I found a paper back, anything I could get my hands on. This is from the 70s, written by a chap called Alan Ashworth for his PhD thesis. Again, actually, weirdly enough, at the University of Nottingham. And he'd been looking at the reactions of sodium and potassium, particularly because, actually, at the time, we were interested in their properties for use in nuclear reactors. And his idea, based on his entire PhD thesis, was that electrons were being lost from the surface of the metal up into the water where they're essentially dissolving. A solution. It seems really weird. We think of sodium chloride, salt dissolving into water, colorless solution. It turns out that electrons can also dissolve in some solvents. The thing is, when they do it in water, it tends to go with a bang, producing hydrogen and hydroxide ions at incredibly, vanishingly small speeds. But just in the 70s, Alan Ashworth caught a glimpse of blue. Blue, the color that we see when we see electrons dissolved in solvents. And this is why I knew I had to get in touch with Phil. Because when I was looking at this high-speed footage, look here, just at the moment of the explosion, blue. On the right-hand side, just at the moment of the explosion, blue. I think we're seeing a tiny fragment of the moment where the electrons are being lost from the metal and being given to that water before we get our bang. I think we're getting to the crux of what's going on with this reaction. But we have a problem. And the problem is, how the hell are we going to get these electrons fast enough into the water to cause that explosion? Because every time we do this, we're giving off some gas, which should be separating the surface of the metal from the place where we want our reaction to happen. The metal also is really hot, also helping to stop the water from the metal making good contact. And this is Phil's brilliant idea that was staring us in the face for decades and decades and decades. Nobody thought to have a think back to their GCSE, their grade 10 model of bonding. What happens? What's holding this structure together? The delocalized electrons, negatively charged, attracting our positive ions. If we move those electrons out into the water, we no longer have those attractive forces holding the structure together, but we still have the repulsive forces, just like two similar-ended magnets holding themselves together. The structure should rip itself apart. Now, there's only one way to know whether or not that's going to happen, and that is to see if you can model it in real life. So, first of all, Phil and his group, they went to the computers. They were theoretical chemists, and they built a model of sodium atoms here in blue, surrounded by water molecules there in red, and within 10 picoseconds, fantastically small period of time, there all sodium had broken down, revealing spikes shooting out into the surrounding water molecules. Can we see this in real life? Well, ladies and gentlemen, now thanks to modern camera technology, we are able to see things at fantastically small timescales. And Phil, up in Braunschweig, with his group, was able to get these images, and you see the fourth image down on the right-hand side, followed by the fifth, is the moment where Phil describes this ball of metal turning into a hedgehog, bursting out into the surrounding water, increasing its surface area, ready to start a reaction. Brilliant. We've reached the frontier of knowledge for humanity. But the story doesn't end there, because actually, it turns out that just because something's blue isn't really good enough for the scientific community to be convinced that what you're looking at is a solvated electron. They needed more proof. And it was around this time that I got in touch with these guys up in Prague, and Pavel, on the left here, Phil's group leader, was telling me that he was receiving a bit of flack because a guy, Steve Bradforth, who he described as Mr. Solvated Electron, was saying basically, listen, Pavel, just because it's blue, I'm not convinced. You need to do better. And I said, well, what's going on? Wait a minute. We've known since the 70s that solvated electrons have been involved in these reactions. Huh? Is this Pavel? Where did you find that? I said, well, I kind of got on Google and I just read anything I could get my hands on. He goes, oh, that's interesting because there's nothing in the scientific literature about this. And I was like, well, of course, I haven't really been able to get onto the expensive databases you guys have access to. I'm just a school teacher, what would I know? But I just read this PhD thesis. He's like, we need to talk to this guy. Let's get in touch with him. So Pavel set about trying to find and track down Alan Ashworth, and the trail went dry very quickly. Sadly, it appears Alan might be dead. So we had to go back and actually start again. And this is where Phil and his group went once more up to Braunschweig and were able to collect the fingerprint of this blue color, proving once and for all this is a solvated electron here. We have reached the boundaries of knowledge for humanity. Thank you very much, ladies and gentlemen. We're going to take the front cover of one of the highest ranked chemistry journals on the planet with our solvated electrons, Angewandte Chemie, last year. So, they very kindly, when they published their paper, gave me a cheeky little mention down at the bottom. Thanks, Mr. Fleming. So, what did What If do for me? What If took me from a school child ready to step out into my boundaries of ignorance through to the boundaries and the frontier of ignorance of humanity itself. And the story won't stop there, because the alkali metals have many, many more interesting properties to reveal to us. So I ask you guys, what happens when you ask, what if? Where will your journey take you? Thank you.